It is hard to speculate at this time which came first, the chicken or the egg, but two things were clear. There is a direct comparison between the relay coils of the historic relay control panel and the memory array in a computer. There is a direct correlation between the wiring diagram of the relay control panel, its logical rungs of logic, and the logical statements of computer programming. Which similarity was thought of first, who knows? The computer was not invented to invent the PLC. Single-board computers were already in use and available when the first PLC was conceived. The exact detail of this history is not a goal of this discussion, but just the general ideas. This graphic illustrates all of the components necessary to provide a control system for a small process or machine: a CPU, central processing unit, random access memory RAM, and a communications port. Okay, first, it is not a computer unless it has a CPU, the central processing unit. This component executes the sequentially stored instructions in memory against the data stored in data structures mapped out in the memory of the computer. RAM, or random access memory, without which there would be no stored instructions or stored data to work with. A communications port, identified here as RS-232, without which there would be no means to download the sequence of instructions and memory map of data structures into the random access memory. This alone gives us enough for the system to think, so to speak, but it is only capable of thinking about the data that we downloaded with the sequence of instructions. How boring. However, there is another path for information to find its way into the computer's memory other than just by means of the communications port. Notice the two columns of screw terminals on both the left and right edges of the circuit board. One is marked inputs and the other is marked outputs. The original controller used octal addressing for the inputs and outputs, as you can see. We have done the same here. The base 8 number system had 8 symbols, 0 through 7. There is not an 8 or a 9 in the base 8 system. Remember, this first position is units, the second is 8s, the next is 64s, then 512s, and so on. In this case, we have units and 8s. 10 means 1-8. So when you see 1-0, if you look at the inputs, it goes 0, 1, 2, 3, 4, 5, 6, 7. Then it looks like 10 through 17. That's not, because this is a base 8 number system. When you get to 7, the next symbol rolls over. So 10 means decimal 8. 11 would be decimal 9, and so on. So 0 through 17, octal would be the same as 0 through 15 decimal. On the bottom edge, we have screw terminals for power and ground. Here we have several limit switches connected to the input side of the controller and several solenoids connected to the output side of the controller. This is conceptually and technically sound, but it was impractical because of the current levels that would be required from a 5-volt DC power supply in order to power 16 individual loads. Not to mention the potential damage to the controller circuit board when shorts occur, and they will occur in the field wiring at some point. We need to use the 5-volt DC power supply not to switch the load, but to switch larger current handling devices that in turn can switch the field loads, and we also need to isolate the field wiring from the controller circuit board. This could be accomplished with a standard electromechanical relay, and in many cases it was and still is. However, let's be a little more progressive in our solution, and instead we'll use solid-state relays, which come inherent with optical isolation. Let's elaborate a little bit with the electrical isolation between the field wiring and the controller itself. This is a simple diagram of an optical isolator. When the appropriate voltage is applied between terminals 1 and 2, the light-emitting diode on the left floods light upon the base of the phototransistor on the right. The phototransistor switches terminals 3 and 4 to a state of continuity or saturation. A dielectric, or the plastic in between the LED and the phototransistor that separates the diode and the transistor, that isolates the two electrical environments. In other words, it isolates the electrical environment of terminals 1 and 2 from that of terminals 3 and 4. A possible isolation rating is 600 volts AC between those two components, or between the two electrical environments represented by pins 1, 2 and pins 3, 4. Lower isolation ratings are acceptable for devices that don't use high voltage. Typically, these solid-state relays are limited to switching 240 volts AC or less. Let's add a few more components to the diagram to illustrate a more complete circuit. The switch, S1, would represent one of the limit switches in the earlier controller diagram, and V1 would represent a field power source that we want to isolate our controller from. S1 closes, allowing current to flow through the LED, D1. The light from D1 causes Q1 to conduct through the input circuitry of our controller, R2. R2 represents the load. In this case, it would be the input circuitry of our single board controller. This isolation allows us to use a higher voltage for our field devices than would be used on the controller itself. So V1 could be 115 volts AC, whereas V2 on the controller itself is TTL or 5 volts DC. Aside from the fact that this manufacturer has their pins numbered different than my optical isolator, in other words, pins 3 and 4 represent the LED and pins 1 and 2 represent the normally open contact or the output. Keep in mind that there are no contacts or coils in this device. It's all solid state. And these devices are referred to as solid state relays, and although they have no direct contacts, they also have no moving parts. This also means that when they are in the off state, because they are solid state, in the off state they have leakage current, as all solid state switching devices do, typically less than 1 milliamp. Here is an example of several variations of solid state relays. The black module is controlled with 5 volts DC logic and will switch up to 3 amps at 240 volts AC. The white module converts a DC input signal to 4 to 16 volts DC range to the 5 volt DC level used by the controller board. The red module is controlled by 5 volts DC output from the controller and will switch field devices requiring 200 volts DC or less at a maximum of 1 amp. The yellow module has a manual switch that is converted to the 5 volt DC input level. Notice that some have 3 pins in place of 2. These are solid state relays that have both a normally open and a normally closed operation. These modules can be mixed or matched and inserted into a circuit board that comes in 4, 8, 12, or 16 slots. This allows you to interface a variety of field voltages into the 5 volt DC environment of the controller. This particular example has IAC, so they're input AC, and then they have some output AC. The black ones are output AC, and then there's 2 blank slots. Looking at our single board computer again, we will place a solid state switch between the output terminal of the controller and the output device. In place of the components shown in an earlier illustration, here we represent the device with the more conventional symbols of a coil and a switch. These solid state relays with isolation are connected between each output device and the 5 volt output signal environment controlled by the program in the controller, which is stored in the RAM. When it goes high, the solid state relay switches the field voltage L1 across the load, in this case 115 volts AC. These devices have absolutely no intelligence, artificial or otherwise. They simply interface 2 different voltage environments. In this case, controller output 5 volt DC TTL level to 115 volts AC line. The exact same device, the optical isolator, packaged a little bit differently, is used to interface interface the input devices to the input terminals on the controller. In our previous illustration, we were interfacing the output of the controller to the output devices like a solenoid. In this case, in this example, we have a 115 volt AC proximity switch that is powered by L1 and is going to switch the input in the controller that's at a 5 volt TT level. When the proximity switch is in an on state or energized, it closes a solid state contact that switches 5 volts DC from the controller back into the controller input. By inserting these optical isolation interface devices between the 5 volt DC logic level of the controller and the field devices, we are able to utilize 115 volt AC field devices in both the input and output scheme of things. By using 16 slot circuit boards, one for inputs and one for outputs, we have a nice clean I/O, that's input-output I/O scheme, for a grand total of 32 inputs and outputs maximum. 16 inputs at any voltage and 16 outputs at any voltage. Now, there is something wrong with this picture. Your immediate reaction might be that a maximum of 16 inputs and 16 outputs isn't going to replace much of a relay control panel that has hundreds of input devices and half again as many output devices. We could always make the controller card larger and put more terminals on each edge and even stack them 3 or 4 levels high. This would function, but this is not a good solution to increase the quantity of I/O devices that you can connect into one controller, especially if you are the one that has to wire it or troubleshoot the wiring. Increasing the footprint of the I/O termination is not the solution. How about if we make more use of the few terminals that we already have? Let's take a closer look at our input interface circuit board with the 16 optical isolators. Notice that there are now 2 circuits in series with each input device, each sensor. And the wiring to the input terminals on the controller circuit board on the right. There are now 2 circuits in series with each input device and the wiring to the input terminals on the circuit board on the right. The first column of circuits, as you can see, are opto-isolators. They isolate the 24 volt DC field voltage from the 5 volt controller voltage. The second column of circuits are all solid state switches, and they are all 16 of them controlled with one signal that is shown unconnected at the upper right corner of the circuit board. You see it in bold line there, and it says it has an arrow that has nothing connected to it. This digital signal, 0 volts DC or 5 volts DC, when applied to this unconnected terminal, effectively by means of this bank of 16 solid-state switches, connects to or disconnects the entire array of inputs. If that bank of 16 switches is turned off, then all 16 of the inputs are completely removed from the orange conductors that represent the plane or the back plane or the bus of the controller. So if there's no signal level on that bank of 16 switches, it's as if these 16 inputs don't even exist. Therefore, to repeat myself, if the signal is 0 volts DC, for all practical purposes, the entire circuit doesn't even exist as far as the controller is concerned. Assuming that the controller knows, by way of its program, when it wants to look at the state of these 16 inputs, we simply add a little circuitry that the controller uses to switch the input card connected or disconnected to the 16 input terminals. So to repeat that, the CPU, by way of the program, knows when it wants to see the state of those 16 inputs. So by way of the I/O controller, it would send a high or a 5 volt DC level, switch all 16 of those solid-state switches on at once, and then the state of all 16 inputs would be felt over to the 16 terminals 0 through 17. Remember, that's base 8 octal. So the controller now has control over whether or not the controller sees those 16 inputs. Now that we have a method of switching an entire array of 16 inputs connected or disconnected to the 16 input screw terminals, we can look at getting multiple use from 16 input terminals. Keep in mind where we're going with this. We don't want to make the single board controller larger. We don't want to add more screw terminals. We want to stick with 16 input terminals on this controller. How might we have multiple input circuit cards like this one, each with 16 inputs, wired to the same 16 input screw terminals without one set of inputs interfering with any other set of inputs? Remember, the controller knows when it wants to look at that card, and by way of the I/O controller, it activates that card, switching it into the input terminals. This gives the controller a method of energizing or activating a specific group of 16 inputs by sending a signal to a decoder by means of a 4-bit line or a 4-bit signal. Now, the only difference between the previous diagram and this one is the decoder. So the I/O controller now, instead of having a single signal, has 4 lines, and 4 lines in binary give you 0 through 15. So you have 16 different combinations of high and low, zeros and ones on 4 lines. That particular decoder, if you look at the ANDs, you see one input is inverted with a little circle on the AND gate. So when the correct ones and zeros comes across those 4 lines, it will activate that card. If we put this decoder at each card location or slot, in other words, if we have more than one of these input circuit cards and all of them are attached to those 16 orange conductors that feed into the controller, and if we put a decoder at each card or slot location, and each decoder is designed to respond to a unique combination of high and low signals on the 4 conductors that are connected to all of the decoders, then each decoder is capable of recognizing a unique signal. And we give our controller a method of sending a unique signal to each possible location or slot to activate an input card. Let's see what this would look like put into action. Here we have 2 input cards, 2 groups of 16 inputs each. They are both plugged into a common bus of 16 conductors referred to as the backplane. The backplane has multiple locations for cards, and each location has permanently attached to that location a unique decoder between the I/O controller and each of the circuit cards. Notice that decoder slot 1 and decoder slot 2 do not have the same logical gates, and these decoders are permanently attached to that physical slot. When the processor needs the state of the 16 inputs, we refer to that as the input image. It's a snapshot of the state of those 16 inputs. When the processor needs the state of the 16 inputs from slot 1, it activates slot 1. By way of the decoder on slot 1, all the remaining decoders do not recognize the signal for slot 1 and do not respond. As you can see, slot 2, because the logic doesn't match up with the highs and the lows, the ones and zeros on the 4-bit control bus, no signal comes out of that decoder. But one does come out of the decoder from slot 1. It activates that entire bank of 16 solid-state switches, which will switch the state of those 16 inputs and put them into a word in memory that is identified permanently with slot 1. You look at the memory location is identified as I for input, colon, that's the delimiter, slot 1, decimal point, word 0. This will be explained later on in the lecture why we show word 0 instead of just showing I:1. Some modules can support more than 16 input devices. They can actually go as high as 32 16-bit words. So then it becomes a matter of input slot 1, words 0 through 31, and then bits 0 through 15. So the controller transfers the state of these 16 conductors to a 16-bit word in the controller's memory. These 16 states represent the 16 inputs wired to the card in slot 1 and are recorded in a 16-bit word in memory. This location in memory is permanently associated with slot 1 inputs or outputs. Now when I say permanently associated, I mean the pointer or the tag name I:1.0 is permanently associated with that circuit card. The processor deactivates slot 1 and then activates slot 2. So we have a different signal now coming over the I/O controller. Because the high-low states on the 4 lines of the control bus is now different, slot 1 does not respond through the decoder, but slot 2 does. And the same cycle occurs. The decoder in slot 2 activates a bank of 16 solid-state switches, and all 16 of those inputs are felt on the 16 orange conductors, and they are moved into a word in memory associated with slot 2. Hence, input I for input colon slot 2 word 0, 16-bit words. Well then, if we can activate input cards one at a time into the 16 input screw terminals on the controller board, we can apply the same technology to the 16 output terminals on the controller board. This processor can only do one thing at a time. It can work with the I/O circuit in memory, or it can execute the program. So why bother doing the same with the output screw terminals? In other words, why create a second data bus and control bus to control groups of 16 outputs? Why not just hook all of the 16-bit cards, inputs and outputs, into a single bus, data bus of 16 conductors going into one set of 16 screw terminals on the processor? Keep in mind, if we add some electronics to the processor, we can read in inputs into memory, and when it comes time to do the outputs, we can read those out of memory out to the cards. You'll see this in a bit. So we're going to plug all of the input and output circuit cards into the same backplane, common bus, and let the processor sort this all out. Okay, let's summarize what we've done here. We've eliminated all but 16 I/O terminals on the controller board. We created a chassis, a physical structure, a rack, that allows us to plug many input and or output circuit cards into a common 16-line backplane. And the processor activates one card at a time. Most PLCs use this scheme for managing the collection of the state of input devices and for controlling the output devices. The active backplane, called so because the processor activates one slot at a time. What separates the PLC from other industrial controllers is this I/O scheme that allows you to use many I/O cards, inputs and or outputs, or combinations thereof, and of many voltage interfaces. This literally was the primary differentiator between a single board computer controller and a PLC. The programming language, ladder logic, used to program PLCs, that would be the second item, and we'll cover that in a bit. It is really a very straightforward, simplistic system when you look at it one function at a time. If you look at this diagram in front of you right now and study it, you will realize that everything external to the processor module, by way of either the control bus or the data bus, is nothing but solid-state switching. You could go to any electronic supplier and buy all of these components to build your own set of decoders, your own set of optical isolator I/O cards, etc. There's no rocket science here, folks. This is a real simple solid-state switching concept. Let's take a look at one input a little bit closer. Examine this illustration of a complete input circuit, one of 16, on a circuit card in slot 7 of the I/O chassis, and its relationship to the backplane of the I/O chassis. The backplane in this illustration is purposefully shown with a minimum quantity of conductors in order to simplify the diagram. There are two connections of interest. One of 16 input isolation circuits connected to one of 16 common runs on the data bus, and the common connection between the control bus at the top of the diagram and the decoder. Remember, the decoder is physically a permanent item at each slot in the chassis. So the decoder is a permanent circuit at each slot and unique to that slot. When the input device is energized, in this case it's shown as a proximity switch in the lower right-hand corner. When the input device energizes, the LED in the optoisolator excites the phototransistor, but the solid-state relay in series with the input device and the optoisolator going to the backplane is not activated. Therefore, the input device can toggle between on and off state without the signal ever being seen on the backplane. That's because this slot has not been activated from the processor. When the processor reaches that phase in its sequence where the image of each input module is to be collected and stored in the controller's memory, the processor will then activate one slot at a time, read in the 16 bits from the backplane into a word in memory associated with that slot. Then it deactivates that slot and activates the next slot that contains an input card, and it does this sequentially in numerical order. Okay, so the slots are activated in order. When slot 7 comes up, a binary 7, that's 0, 1, 1, 1, is sent down the control bus, activating slot 7, and all 16 solid-state relays are energized together, placing the state of each input device directly on the backplane. The processor transfers the state of the 16 conductors of the backplane into a word in memory set aside just for the inputs of slot 7. Remember, that was word I:7.0. This diagram is slightly different than the previous one because it represents the relationship between the backplane and a single output. The previous diagram was for an input circuit. This is an output circuit, one of 16. This is an output, and its state was stored in memory by the rung of logic that controls that output. So in this case, we're not sending something to the controller. The controller is sending something to the output. The processor writes the state of these outputs across the backplane to all of the modules. When the slot is activated by its decoder, and even though the 16 outputs are all felt at all slots on the backplane, only one slot is activated. This means that at any moment when the processor is working on the backplane, that it is the processor and a single module that are connected. All of the other modules, while plugged into the chassis, are electrically unplugged by the bank of solid-state relays in each card that isolates the I/O from the backplane. So, in the case of the outputs, the data or states, which are stored in memory as a result of the logic, are placed on the backplane by the processor before the slot is activated. The states are felt at every connector on the backplane, but without any of the I/O modules activated, it goes no further than the backplane side of the solid-state relays in each card. After the states are put on the backplane by the processor sends a slot number down the control bus, in this case a binary 3, 0011. This activates slot 3. The activated card connects the 16 states on the backplane to the output circuitry via the solid-state relays in the holding circuit. When the processor deactivates this slot, we can't have the output turning off again, so we need a device that will hold the last state sent by the processor. That's what the holding device is. So there it is, the active backplane. This is all there is to what transpires on the backplane between the I/O modules and the processor. It is, in its entirety, an array of solid-state switching designed to switch multiple I/O interfaces on and off of a common bus connected to the processor's input-output terminals. Remember, we did have input terminals and output terminals. So the 16 conductors on the back of the processor module are I/O terminals now. There are, however, a few points that I would like to add to this. Only 8 conductors are shown here for the data bus on the backplane to represent 16 that actually exist. There's actually quite a few more lines than 16. There's support lines for voltages, grounding, and other purposes. Only one 16-bit word of data can exist on the backplane at any given instant. Don't forget this. Only one 16-bit word of data can exist on the backplane at any given instant. If the I/O card supports 32 inputs or outputs, they are still handled 16 bits at a time. Each 16 bits is one word. So a 32-bit card has 2 words associated with it in memory. So 32 inputs or 32 outputs would be handled one word at a time. So a card that has 32 inputs takes the same amount of time as 2 cards, each with 16 inputs. If you use a 32-bit card, circuits that have 32 inputs or 32 outputs connected to the card, the processor activates the circuit card twice, once for each group of 16 bits. If it is a DeviceNet scanner circuit card that has 32 words of inputs and 32 words of outputs, 32 individual transactions will take place one at a time on the backplane when the processor is collecting input images, and the processor will store these 32 words one at a time in 32 unique words in memory set aside for that slot. So we'll say that it was slot 5. It would be then I:5 dot word 0 through word 31, and each word has 16 bits. And when it comes time to send out the output states, which are stored in memory as a result of the logic, to that slot, it will be one word at a time until all 32 words are transferred from the processor's memory into the memory in the DeviceNet scanner card's memory. This sequence is repeated to transfer the 32 words from the controller's memory to the 32 words in the DeviceNet scanner card for the outputs. One of the most popular PLCs will support 30 slots of I/O. Each slot will support 32 words as inputs and 32 words as outputs. That is a total of 1,920 words, or 30,720 unique bits trafficking on the backplane each processor cycle. It is sufficient to say that all I/O modules on the backplane are dumb as a brick. They do no thinking and no processing. They are simply no more than dumb switch banks that are activated one at a time to collect images of the states of groups of 16 inputs or outputs, and to collect other information or transfer the results of logic out to the actual output.